Welcome to my lesson on relatively prime numbers. This is one lesson in a series that I've been presenting. Four of them have already been posted, and this one relies a little bit on some of the earlier lessons. So just as a warning, you may want to at least peruse the earlier lessons in the playlist and see if there's any topics there that you're not familiar with, in which case you may want to listen to those other lessons first. In our first problem, we have two parts to it. Prove that the GCD, and that's the notation I've been using. So a lot of times you'll see GCD and then the two terms in a bracket, but I'm kind of taking a shorthand approach here. So the GCD of 2k plus 1 with 9k plus 4 is 1 for every k being an integer. And then the second part is to determine the GCD of 2k minus 1 with 9k plus 4 in terms of k. Okay, so just as a reminder, the integers a and b are relatively prime. Sometimes the term coprime is used, but I think relatively prime is more common. If their greatest common divisor is 1, in other words, if the greatest common divisor written here in notation equals 1. Okay, so those are the problems. I have a hint on this slide, and then I'll go about giving you the solution on the following slide. So if you don't want to see the hint, you may want to pause right here. If you want to see the hint, then let me show you that, and then you may want to pause before I go into the solutions on the following slides. Okay, so here's the hint. If D divides M and D divides N, then D divides any linear combination of M and N. In other words, this here. And this slash means divide. And when you're talking in terms of number theory, when you say divide, you mean exactly. So in other words, 3 divides 9 because it goes into it exactly. Of course, you could divide 3 into 10, and if you're talking about rational numbers, but in number theory, it has a more specific meaning here. It means divide exactly. You would have seen that in my earlier lectures, but just in case you're joining at this point, I'll mention that. Okay, so if you want to give these a try, pause here, and then I'll do the first one on the next slide, and then the second part on the slide after that. In part 1 of our problem, we want to prove that for every integer k, the numbers 2k plus 1 and 9k plus 4 are relatively prime. Consider the following linear combination of these two numbers. So we'll take 9 times the first number minus 2 times the second. And the k terms cancel out, and then you get 9 minus 8, which is 1. So if D divides, and recall the hint I gave you from the previous slide, if D divides 2k plus 1 and 9k plus 4, it must divide all linear combinations, including this one here. Thus, D divides 1, which implies D is equal to 1. So the GCD of 2k plus 1 and 9k plus 1 is 1. The second part of our problem is for numbers 2k minus 1 and 9k plus 4, find their greatest common divisor as a function of k. So we consider the linear combination of these two numbers. We'll take minus 9 times this first number plus 2 times the second, and we get 9 plus 8 equals 17. The k terms cancel. So if D divides these two numbers, it must divide this linear combination. That was the hint I gave you on the first slide as part of the problem. So D divides 17, and the GCD could either be 17 or it could still be 1. So we need to determine when these cases happen. for what value of k is 2k minus 1 a multiple of 17? In other words, 1 is 2k minus 1 equals 17n for some integer n. We can solve this for k, and we get k equals 1/2 17n minus 1. And we want to know when that's an integer. And that's when n is odd, because you have an odd number times an odd number, which is odd. You subtract 1 from it, you get an even number, and that's divisible by 2. So let n be odd. Let's say it's of the form 2m plus 1 for some integer m. Then we plug that back in for n. And we get k equals 17m minus 8. And then we plug this result back into 9k plus 4 to see if it's a multiple of 17 or not. Turns out it is, but let's check. So we plug this in for k, which I've shown here. Then we multiply through by 9 and add 4 to it, and we get this here. And then, in fact, 17 can be factored out of both of these terms, and we get 17 times 9k minus 4, which is always divisible by 17 because of this factor here. So two numbers have a GCD of 17 when k is of the form 17m minus 8 for some integer m. Otherwise, they have a GCD of 1. Okay, so that's this answer. And then just to have a couple of examples of this, let's take m equals 1. So we're in this case here. Then k would be 9. 2k minus 1 is 17, and 9k plus 4 is 85. And you can see here that 17 divides this number clearly, and then 5 times 17 is 85, so it divides this also. And let's test the other case where k is not of this form here. So we'll take k equals 2, and we get 2k minus 1 is 3, and 9k plus 4 is 22. So again, we're not divisible by 17, we're divisible by 1 in this case, so it fits our what we've determined through our analysis here. I have a few theorems on the following slides which we can use in the solution of yet other problems. So let's look at the first one. An equation of the form ax congruent to b mod m has a solution if and only if the GCD of a and m divides b, where a, b, and m are integers greater than 1. So since this is if and only if, we need to prove it in two directions. On this slide, I'll prove it in the forward direction. Assume there exists an integer x sub 0 that satisfies the congruence, this congruence here. By the definition of congruence, ax sub 0 minus b must be a multiple of m. In other words, we can write it this way here, and we can rearrange it into this equation here. A times x sub 0 minus my equals b. Okay, then let d be the GCD of a and m. By definition, the greatest common divisor divides both a and m. So we can write a is d times some integer j, and m as some product of d times some integer k. And then we plug these back into here. So you notice we have dj for a, and then dk for m. So we have this here, and that equals b. And then we have a d in here and a d in here, so we can factor that out. But everything inside of here is an integer, j, x sub 0, k, and y. So we have d times an integer equals b. Therefore, b is a product of d with an integer, and that implies that d divides b, which is what we wanted to show in the forward direction that the GCD, which we call D, divides B. So we've proven it in the other direction, forward. Now we want to go in this direction. If the GCD of A and M divides B, then we want to show that this equation has a solution. So I'll do that on the next slide. We want to prove the theorem in the opposite direction. So assume D divides B, where D is the GCD of A and M. This implies that B can be written as the product of D times K for some integer K. What we want to prove is that there's a solution to this equation that I'm pointing to down here. So what we'll do is make use of something called Bezout's identity, which is quite useful, and we'll see it in other problems that we look at later on. So for integers A and M, where the GCD of A with M is D, there exist integers S and T such that AS plus MT equals D. Now if we multiply both sides of this times B, K, which I've shown here, then we get K times this plus K times D, but we know that's B. We're trying to get it into this form here, so that's kind of the direction we're going. Then we just multiply this out, we get ASK plus MTK equals B. Then we do a little bit of rearrangement. We subtract the B from this side and subtract the MTK from the other side. So we have this here. Then we let X equal SK. Then the above equation could be written as AX minus B equals M times minus TK. Since minus TK is an integer, the above equation implies that AX minus B is a multiple of M. In other words, AX is congruent to B mod M, and thus X equals SK is a solution of the above equation, which is what we wanted to prove. So we have proven our theorem in two directions. I have another theorem here that we'll make use of later on. If the GCD of A and B is 1, then A has a multiplicative inverse modulo B. So for our proof, we want to show there exists an integer X such that X times A is 1 mod B. That's what it means to be a multiplicative inverse of A mod B. That when you take the product, it equals the identity, the multiplicative identity. So we'll make use of Bezout's identity again, which states for any non-zero integers A and B, there exists X and Y such that AX plus BY equals the GCD of A and B. And we're given that the GCD of A and B is 1, so we can make use of this above identity. Was the GCD of A and B being substituted in is 1. So we get AX plus BY equals 1, or we can write that as AX equals 1 minus BY. And in terms of modular arithmetic, this is the same as this here. We have the minus Y times B, so we can write it this way here. And in other words, X is the multiplicative inverse of A modulo B. Let's have a look at another problem. If A and B are distinct integers and K is a positive integer coprime, i.e. relatively prime, to A minus B, then prove there exist infinitely many n, integers n, such that A plus Kn and B plus Kn are relatively prime. Before we get to the solution, let's look at an example. Sometimes it's helpful to check some specific numbers in a problem or a theorem to get an idea as to how you might do the general proof. And that's what we'll do here. So I'll take A equals 2, B equals 5, K equals 7. Then we want to check that the GCD of A minus B was K is 1. So a minus b is minus 3. Don't let the minus number bother you. And then k is 7. So the GCD of these two numbers is 1. That's still the largest positive number that divides both of them. Then we just plug in 2, 5, and 7 for a, b, and k. And so we get a plus kn equals 2 plus 7n, and b plus kn equals 5 plus 7n. And we want to determine n such that the GCD of these two numbers is 1. And we can simplify this using the Euclidean algorithm property, which says the GCD of x and y is equal to the GCD of x with y minus x. So we'll let this first term be x and this second term be y. Then we get x here, and then x, y minus x is this minus this. That's 3. So we want to know when, for what value of n this equals 1. Since 3 is prime, the GCD of these two numbers is either 1 or 3. And it equals 3 when 3 divides 2 plus 7n. And when 3 does not divide 2 plus 7n, it equals 1. So let's look at the case, or try to figure the case out, where 3 does not divide 2 plus 7n, for what values of n. And that'll tell us that's when the GCD is 1. And then the other case, of course, would be when the GCD is 3. So to determine when 3 does not divide 2 plus 7n, we work in modulo 3. So we want to convert this to mod 3. 7 is congruent to 1 mod 3. And then you just multiply this, both sides here, by n. And you get 7n is congruent to n mod 3. And then, of course, 2 is just congruent to 2 mod 3. Then you add these two together, and you get 2 plus 7n is congruent to 2 plus n mod 3. 2 plus 7n is not congruent to 0 mod 3, if and only if 2 plus n, the thing it's equal to, 2 plus n is not congruent to mod 3. And that happens when n, just taking the 2 to the other side, that happens when n is not congruent to minus 2 mod 3, which is the same as n not being congruent to 1 mod 3. So the condition that n is not congruent to 1 mod 3 is equivalent to n being congruent to 0 mod 3 or 2 mod 3. Those are the only 3 cases. So if it's not this case, it has to be the other 2. So in these 2 cases, the GCD of 2 plus 7n and 3 is 1. And then otherwise, the GCD of 2 plus 7n and 3 is 3. Okay, so that may give us some insight as to how we would go about solving the problem where we just have a plus kn and b plus kn, and we want to know the conditions under which, for n, when the GCD of the two numbers is 1. So we'll look at that in the next slide. Let's continue with our problem using some of the ideas that we had in our example from the previous slide. So I copied the problem here again at the top just to remind us. So if a and b are distinct integers and k is a positive integer, coprime, i.e. relatively prime, with a minus b, then prove there exist infinitely many integers n, such that a plus kn and b plus kn are relatively prime. So we'll make use of the Euclidean algorithm just as we did in the example. We'll take our two numbers and then let the first one equal x, the second one equal y. So this GCD equals this GCD. And then we just do the subtraction here and we get this here. And then we'll let d equal a minus b just to simplify the notation. So we want to know when, for what values of n does this equal 1? Which is what I just wrote here. A sufficient condition for two numbers to be coprime, relatively prime, is for one number to be congruent to one modulo the other. I'll prove this on the next slide. It's not too hard, but it's not immediately obvious, so I'll prove that on the next slide. And then I'll continue with the proof after that. Therefore, if we can find n such that a plus kn is congruent to 1 mod d, then it must be true that the GCD of a plus kn d is equal to 1. Okay, so let's prove this first. I'll do that on the next slide. So let's prove the statement I made on the previous slide. If x is congruent to 1 mod y, then the GCD of x and y is 1. That's what I had claimed. And it's not too hard to prove, but it takes a little bit of work. We'll do that here. So by the definition of modular congruence, if we're given this, then that implies there exists some k such that x equals ky plus 1. And we can write that as x minus ky equals 1. And then let g equal the GCD of a and b. By definition of a greatest common divisor, g must divide both x and y. Since g divides y, g obviously must divide k times y, where k is just an integer. Since g divides x and g divides ky, g must divide the linear combination x minus ky, but that equals 1, so g must divide 1, and that implies that the GCD of x and y, which equals g, is 1. So let's finish up the derivation. We left off with step 2, and we had this congruence, which I want to write like this here, and then we're going to make use of theorem 1. If you notice, this fits the mold of theorem 1. We have the k identified with a, and n identified with x, b is 1 minus a, and then m is d. If you recall, d we defined to be a minus b. And so in order to use this theorem and claim that this has a solution, and in turn this has a solution, we have to demonstrate that a m divides b, or in our case, k d divides 1 minus a. But that follows pretty easily. Since we're given that k is coprime with a minus b, that means, which is d, we know that the GCD of k and d is 1, and since 1 divides every integer, including 1 minus a, we meet the requirements of this theorem, which implies that we do have a solution in terms of n. So that only gives us one solution. In order to prove that there are infinite many solutions to our problem, we can do that. And since the GCD of k and d is 1, k has a multiplicative inverse modulo d. That was the second theorem we proved a little while back. And let's call that multiplicative inverse k minus 1. Then we can just multiply this times both sides of this equation here. And we have n equals minus k to the minus 1 times 1 minus a mod d. So this describes a congruence class. It's all numbers of the form shown here. You just have this, then plus some multiple integer multiple times d, but there's an infinite number of integers, so we have an infinite many values for n, and thus we have an infinite number of solutions to our problem. What you might want to do is go back to the example we did and plug numbers into here and see if you can reason to our solution that we got previously for this specific case using this general solution we had here. Okay, so that was it. It was a rather difficult problem, but it illustrates a lot of points, and we made use of a couple of theorems that we proved earlier. So you can see how number theory builds on earlier results, and it just becomes, more and more involved as you dig deeper into it. I have one more problem in this lecture, which I'll get to on the next slide. So we have one more problem in this lesson. Prove that the fraction 14n plus 3 divided by 21n plus 4 is irreducible for every natural number n. This problem was the first problem in the first International Mathematical Olympiad in 1959. And I'll give you a hint. If you don't want to see the hint, you may want to pause here. Otherwise, I'm going to show you the hint in a second. Okay, here's the hint. Consider the property that if D divides both A and B, so for example, it's the GCD of A and B would be an example of such a D, then D must also divide any linear combination of A and B, i.e. D divides AX plus BY for integers X and Y. Okay, so that's the hint. I'll give you the solution on the next slide, and then I actually have a second solution, which I'll give you also. Okay, here's the first solution. So to prove that the fraction is irreducible, we must show the numerator and the denominator are relatively prime, coprime, for all integers n. In other words, we need to show that the GCD of the numerator and denominator is equal to 1. And just as a reminder, irreducible means that you don't have any common factors in the numerator and denominator. So for example, 4 over 8 is reducible because you can divide a 4 into the numerator and the denominator and get 1/2. So we want to show irreducible for these two terms here. So using our hint, consider the following linear combination: 3 times 14n plus 3 minus 2 times 21n plus 4. Then this gives us 42n plus 9, and this gives us 42n plus 8. And when we subtract it, the 42n's cancel, and then we just get 9 minus 8, or 1. Thus, the GCD of these two numbers must divide 1, which implies that the GCD of the two numbers is 1, right? That's the only option you have. And since the greatest common divisor is 1, the fraction cannot be simplified further regardless of the value of n. In other words, it's irreducible. Okay, so that was one proof. I have another proof on the next slide. So here's an alternate proof, or a derivation. So we want to show that the GCD of these two numbers is 1. And we use the Euclidean algorithm. If you recall, we take one of the terms, and then we take the other term minus a multiple of the other term, and the two GCDs are the same. So we'll just take minus 1 times this term and subtract it from the first term. When we do that, we get this equals this equals this here, just doing a subtraction. And then we need to apply the Euclidean algorithm a second time. So we bring our 7n plus 1 here, and then we subtract 2 times this from the other term, and that gives us a 1. And of course, the GCD of a number and 1, the only choice, of course, would be 1. That's the biggest number you could divide into two of them. So that's an alternate proof. Okay, so that's the last problem in this lesson, and I have 3 lessons on prime numbers, which I'll eventually record and then post on YouTube.